Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below. So today, we are setting up a real classroom vibe for this deep dive.
Yeah, a bit of a masterclass today.
Exactly. We are teaching a masterclass on industrial furnaces, and we are going to explore the biggest pain points, the mathematical traps and the real-world structural issues that engineers just keep running into.
Right, because I want to speak directly to you, the listener, for a second. Whether you are designing this massive steel slab reheating furnace or just a small batch processor, the laws of thermodynamics remain brutally unforgiving.
Oh, absolutely. They don't care about your design intentions.
No, they don't. So the goal today is to help you avoid the most common and honestly the most extensive design mistakes.
I mean, I always think of designing a furnace as trying to build a perfectly sealed oven that also somehow has to behave exactly like a jet engine.
That is a great way to put it.
Right, because even a tiny miscalculation can warp structural steel or just waste millions in fuel. So let's get into our first lesson.
Yeah, let's start with the math.
Well, specifically the false precision trap, because it seems like engineers overcomplicate the calculations right out of the gate.
They do. It is the single biggest misconception engineers make. We love precision, We love carrying our math out to 5 decimal places.
Because it feels safe.
Exactly, it feels accurate. But in furnace design, those calculations are based on highly variable assumptions.
Like what kind of assumptions?
Things like the thermal properties of the materials at extreme heat or the view factors, they constantly shift.
So are you saying we should just guess?
Well, no, not just guess. It is about recognizing probable error.
Okay, make sense for me.
You have to know when an approximation actually saves time without adding to the margin of error in your final design. A perfect equation means nothing if the physical reality of the furnace is shifting.
Which is a perfect transition to the actual physical structures. Because a massive pain point in the real world is differential expansion.
Oh, differential expansion is a structural nightmare.
Because the hotter inside walls expand so much faster than the colder outside walls.
Right.
So the whole wall just bulges inward.
Right, and the misconception is that engineers often try to fix this by just brute forcing it. They make the walls thicker or they specify these heavy-duty solid bricks.
Thinking more mass equals more stability.
Exactly. But you cannot fight physics. The better solution is completely changing the material strategy. You use cast or rammed refractories.
And those are fired right there in place.
Yeah, and the brilliant part is that they actually develop physical discontinuities during their initial shrinkage.
Wait, discontinuities, like cracking?
Yeah.
Because my instinct is that cracking is a structural failure.
Normally it is, but here it is engineered flexibility. Those cracks provide the exact room needed for expansion during the heating cycles.
That is wild.
Or, if you absolutely must have expansion slots, you pack them with a ceramic fiber that stays resilient. It acts like a sponge.
So you build the flexibility right into the material.
Yeah.
But let's talk about the condensation issue, because this blew my mind.
Yeah, the hidden danger of over-insulating.
Right. If you use a sulfur-bearing fuel and you over-insulate to save energy, you could actually rust the furnace from the inside out. How does that even happen?
It is a brutal trap.
Yeah.
Because if you heavily insulate, the temperature at the outer steel casing drops significantly. And if that outer casing drops below the dew point of the sulfur dioxide in your flue gas, that gas condenses.
So it turns into literal acidic liquid right against the cold steel casing.
Yes, it condenses inside the wall, destroying your structural steel.
So what is the fix? Because you still want to insulate to save energy, right?
I do. The fix is designing a continuous metal membrane buried within the wall layers.
Oh, like a vapor barrier.
Exactly. You find the depth where the temperature is always above the condensation point, and you place the membrane there to physically stop the acidic vapor.
Wow. You solve a thermal problem and create a material science problem. Let's move on to lesson 2, which is the heat transfer headache.
This is the big one.
Let me play this student here. Heat transfer in a furnace is just the hot walls radiating heat to the cold metal. Right, like a broiler.
That is what everyone thinks, but it completely ignores the complex reality of gas radiation.
Wait, the gas itself radiates heat.
Oh, absolutely. Combustion gases, specifically things like carbon dioxide and water vapor, are not just hot, transparent air. They actively radiate heat.
So how do you even calculate that in the real world?
Well, we look at the Stefan Boltzmann radiation equation, but applied realistically.
So walk me through the math on that.
Okay, so the heat flux Q over A equals 0.1713 multiplied by the combined emissivity absorptivity factor, multiplied by the view factor, multiplied by the difference between the source temperature to the fourth power and the receiver temperature to the fourth power.
To the fourth power.
Yes, calculating those temperatures in degrees, Rankine divided by 100.
So if it's to the fourth power, a tiny drop in temperature means your heat transfer just falls off a cliff.
Exactly. That exponential relationship is everything.
Do you have a real-world example of that gas radiation in action?
Sure. Take a look at luminous flames versus non-luminous gases. Luminous flames are filled with tiny carbon particles that act almost like solid bodies radiating heat.
Oh, like glowing soot.
Yeah, exactly. They radiate continuously. But non-luminous gases are completely different. To maximize efficiency, you have to calculate the mean emissivity.
Because the gas radiates in all directions, right?
Yes, it radiates to the walls absorb it, and then they re-radiate it back to the load. It is highly dynamic.
Okay, so moving to lesson 3. We've got all these radiating gases, but now we have to get them out of the furnace. Let's talk stack sizing.
Fluid flow dynamics, everyone's favorite subject.
Right, and the misconception here is that a lot of engineers just use a rule of thumb for mass velocities, right?
Yeah, they get lazy with the math.
So they might just assume, say, a mass velocity of 2,000 pounds per hour per square foot for 1,500-degree flue gas.
And blindly using that rule of thumb is a massive mistake. Let me walk you through why.
Please do.
If you use that lazy 2,000 number, you might design a 12-foot diameter stack that is 102 feet tall.
Which is a giant, extremely expensive piece of steel.
Exactly. But if you actually do the fluid flow math and optimize it, you can double the velocity head.
Wait, explain velocity head for a second.
Think of it like intentionally creating a slight pressure drop to increase the velocity of the exhaust fluid.
Oh, like putting your thumb over a hose.
Exactly. So if you double the velocity head, your mass velocity jumps from 2,000 to 3,000.
And what does that do to the physical stack?
Your required diameter shrinks to 9.8 feet. And your height only bumps up slightly to 110 feet.
Wow, so the total outer surface area of that steel stack shrinks drastically.
Yes. You are saving massive amounts of construction capital just by not being lazy with your math.
That is a great takeaway for the listener. Do not let lazy math inflate your building costs.
Precisely.
All right, let's jump into lesson 4. We pulled the most popular internet questions about furnace design.
I love these.
Here's the first one. How do you calculate heating time without burning the outside of the load?
Oh, that is all about non-steady-state conduction.
Because the core is colder than the surface, right?
Right. You cannot use standard steady-state equations. The surface heats up instantly, but you have to push that heat to the dead center without melting the outside.
So how do you do it for a big, complex block of steel?
You have to use the Newman method. It calculates heat flow paths in multiple directions.
How does that work, like intersecting lines?
Sort of. It takes one-dimensional heat flow, so X, Y, and Z axes, and multiplies those factors together. It lets you safely tailor a heating curve for complex three-dimensional shapes.
Oh, I see. That makes total sense.
Yeah.
Okay. Question 2. Is a perfectly uniform temperature the most efficient way to run a continuous furnace?
Absolutely not.
Really? Because my instinct was totally yes on that one.
It is a huge misconception.
Yeah.
If you keep it uniform all the way to the exhaust end, your flue gases leave way too hot. You are just venting wasted fuel into the sky.
So what do you do instead?
You want a variable profile. You start with a preheat zone.
And that's where the cold load comes in.
Yeah, and sometimes it is completely unheated except by the exhaust gases flowing backward. It pulls heat right out of the waste gas.
That's brilliant.
Then you hit the high-temp firing zone in the middle, and finally, a soak zone at the very end.
What does the soak zone do?
It balances the core and the surface temperatures of the load. It lets the internal heat catch up so the metal is uniform, even if the furnace chamber itself isn't.
So you're essentially using the exhaust to do free work.
Exactly.
Which brings us to the last question perfectly. What is the best way to stop wasting heat out the exhaust?
Oh, recuperators and regenerators, no question.
And these have changed a lot over the years, right?
They have. The industry used to rely on ceramic crossflow recuperators.
But ceramics crack under thermal cycling, don't they?
Yeah, they leak over time, the joints open up, and you get fresh air mixing with dirty exhaust. So the shift has been toward metallic concentric tube recuperators.
I always picture those like a thermal traffic circle.
That's a good way to look at it.
Because you have the hot outgoing exhaust gas on the outside and the cold incoming combustion air on the inside, right?
Right.
And the incoming cold air just steals the heat right through the metal wall from the exhaust gas. It preheats the air and saves massive amounts of fuel.
Yes, it directly recovers sensible heat that would otherwise be completely lost.
Amazing. Okay, well, we have covered so much today. The math traps, the structural bulging, gas radiation, stack sizes. But let's look at the future.
Yeah, I want to leave the listener with one final kind of forward-looking concept to ponder.
Let's hear it.
We have spent this whole time talking about optimizing heat and physical structures. But what happens when the fuels themselves change?
You mean as natural gas supplies dwindle?
Exactly. Industries are going to have to pivot to synthetic fuels or coal gasification products.
Right.
But to use those in your highly optimized furnace, you have to precisely match what is called the Wabi index.
The Wabi index, what does that do?
It basically ensures the new synthetic fuel behaves exactly like the old fuel physically inside the burners.
Oh, I see. Because if the chemistry is lighter or heavier, the flame shape changes.
Yes. And if you don't match that index, your precisely calculated radiation profiles and heat transfer coefficients will completely collapse.
Wow. So all that math we just talked about gets thrown out the window.
Entirely. The furnaces of tomorrow will not just be about managing heat. They will be about dynamically adapting to shifting fuel chemistries.
That is a phenomenal thought to end on. Designing for shifting chemistry, not just heat. Well, if you got something useful out of today's episode, hit follow and drop a like. It helps grow the show and keeps the engineering knowledge flowing.